Okay, we are into our very last section of chapter 1 of Griffiths. There are still quite a few chapters to go, but this is going to do it for chapter 1. Our last section is the uncertainty principle. Probably heard of this even if you've never done anything in quantum mechanics. It's a pretty common thing, the Heisenberg uncertainty principle. If you're a fan of Breaking Bad, this is where Heisenberg came from. So what this principle states is right here. So we have like our standard deviation in x. So that would be like our spread of position. So how much is our position unknown? What's our uncertainty in our position? Times our standard deviation in momentum. So we have in real space and we have in momentum space. One standard deviation multiplied by the other standard deviation, that has to be bigger than h bar over 2. So we have a minimum amount of spread that is possible to have in our system. So, in other words, if I know the position of the particle very well, so my standard deviation in x is very, very small, then that affects my standard deviation in momentum space. So I can go ahead and divide both sides by my standard deviation in momentum space. And I could do the same thing for my standard deviation in momentum. So if I make a very precise measurement of my real space so that sigma x is very, very small, in order for this number to be very, very small, that means that sigma p has to be very large. We can think about it another way. If sigma x is very, very small, now we have h bar divided by a very, very small number, which gives us a very large number. So the standard deviation in real space and in momentum space are inversely proportional. So a good example of this is like if you have a wave. So if you're standing on one end and you're swinging this guy up and down and you're making a wave. And then as Griffith puts it, if somebody asks you, well, where is the wave? He said, if somebody asks you precisely where is that wave, you don't really have a good answer. Because, well, here in our picture, our wave is existing between 10 and 40. I don't have a good answer for where the wave is. But if you ask me what is the wavelength, peak to peak being lambda, I could give you a very good measurement of what lambda is. We can contrast that to the idea of, say you send a pulse through a wave. Now in this case, I can make a very good measurement of where the wave is, but I only have one peak here, so I can't give you a very good idea of what the wavelength is. So there's basically a trade-off. We can either have a very well-defined position and a not well-defined wavelength, or we can have a well-defined wavelength but not a well-defined position. And this is going to put it into terms of the Dubrow formula. I believe that's how you pronounce that name. And the Dubrow formula gives us a relationship between momentum p, Planck's constant h, and lambda. So momentum and wavelength are inversely proportional. If momentum is a big number, then wavelength must be a small number, and vice versa. So since those are inversely proportional, that means that we have this trade-off. Now, mathematically, this does come from Fourier analysis. So this comes from taking a Fourier transform of going into position space to momentum space, or from real space to K space. So we will get into that later in later chapters, but for now this is just the basics of the uncertainty principle, and we'll look into actually calculating it out in the last problem of chapter 1, which is problem 1.14, where we know that sigma is the square root of expectation value. I probably got these mixed up, but we can actually calculate what our uncertainty is. And then we can find if, test this relationship if it's bigger than h bar over 2. Now the absolute minimum it can be is h bar over 2, and that happens to be for a harmonic oscillator. Every other case, the uncertainty in x and in p is going to be bigger than h bar over 2. So when I first learned, well, not when I first learned it, when I learned it again in graduate class, my graduate school quantum mechanics class, our professor wanted to start his lecture, so he wanted to get into the proof that uncertainty principle comes from Fourier analysis. So we go from x to say 1 over x, and then we get a certain spread. So he wanted to start the lecture with asking us for examples of uncertainty principles. What is an example of an uncertainty principle? And our professor was a little bit rotund, and he would always wear like a nice button-down shirt to lecture. Well, he was wearing his normal shirt that he changes into for lecture, but underneath his belly he had missed a couple buttons. So basically his shirt was buttoned, and then underneath the belly where he wasn't able to see, it was open. So he started the lecture asking us, do you have any examples of uncertainty? And so one of the students answered, like for example would be if you know your pants are zipped up, but you are uncertain that your shirt is buttoned. And he said, no, that's classical example. We want only quantum mechanics. So yeah, your shirt and your pants are not a quantum mechanical example, and apparently that example did not work for him because it was not mathematical, and that wasn't where he wanted to go with the lecture. Halfway through the lecture, he realized that his shirt was open, and he did fix it. But that's it for uncertainty principle for now. We're not going to get into the mathematical proof until later. And next time we're just going to work on problem 1.14.